This. Okay. Okay. Let's begin today's lecture. In previous lecture, we talked about the power flow analysis. We actually started talking about the effect of how we could analyze the effect of inverters from system perspective, and we started with talking about the power flow analysis, which is one of the steady state analysis for the system, for the power system to be run and find out what is the distribution of the energy and power look like and how the system would behave to address the variation in the load and generation and keep up with the uh, generation demand balance. Now, so far, all the discussion that we had was in general case. So it was a conventional general power system, okay, and all the formulas that we saw, all the methods that we gone through was the general method that we could use on a conventional power system dominated by rotary machine resources. Okay, so far we didn't add the effect of the IBR. Today, we are going to talk about what would be the IBR's effect on the power flow analysis, okay? And how the difference between the inverter-based resources and the rotary machine-based resources would affect that analysis. Now, before I start, is there any question regarding the general power flow analysis? Okay, no question in the Zoom meeting too. Okay, so let's start. Now, let's see what would be what would happen if we have a notable amount or a high penetration level of inverter-based resources in our power grid system. So what would happen in a power flow analysis when the inverters are dominating the system? Okay, now let's start by mentioning the differences between rotary machine, or for example, here, as you can see, synchronous generator, okay, and an inverter-based resources, okay? In synchronous generator, as we know, first of all, in synchronous generator, we inherently produce balanced voltage waveform, okay? Because of the electromechanical structure, it's always we have a symmetry in our waveform. It's a balanced waveform, meaning the half cycles are similar to each other. Okay, there's a symmetry between them. Now, again, we already talked about that, and we talked about the importance of that. The synchronous generator or rotary machine in general would provide a natural inertia because of their mechanical momentum that they have, the inertial momentum that they have. They provide a natural inertia for the system to address any kind of variation or turbulence happening in our parameters in the system. Okay. Now, next step is that they offer voltage and frequency support. That again is based on their natural behavior and how they work. How they do that? Since they have that inertia, okay, they can provide or inject energy in a form of reactive power if needed to stabilize the voltage level. We already talked about that. The voltage and reactive power are connected to each other. Okay, so if we can provide an adequate amount of reactive power in both direction, consumption or generation. Okay, that means we are able to stabilize the level of the voltage in our system. Now, inertia in the rotary machine would provide that. Another part is the frequency regulation, which we said this is another criteria for having a stable system, the stable frequency. Now, again, synchronous generator, or in general, rotary machines, okay, because of their mechanism, how they work, okay, the theory and the technology behind them, okay, they always work at a certain frequency that we define. Now, if they are overload, they could compensate very fastly using their inertia and adapting to the new kind of like setting in near time. Okay. And if they are under load again, they could uh, put that extra generated energy into their inertia for short time, like instantaneous response, and again adapt their situation, their condition to the new demand. So rotary machine, because of the natural mechanism of the electromechanical kind of like energy conversion that's happening constantly in that generators, they could inherently offer a support to maintain the voltage and maintain the frequency at a certain level. Now, uh, they also include an internal voltage. If you already passed a course about the AC machine, you know what I'm talking about, but we have a stator and we have the rotor, and the induction voltage inside the rotor that happens because of the Faraday's law, if you remember about the concept, would create an internal voltage inside the system of the rotary machine generators. And that voltage is actually alternative current, like AC type of the voltage. Okay. As well as because of that structure, they already have an actual reactance in them because they are wires wrapping around the core. So basically there is a huge level of inductance, okay, inside the rotary machine. Okay, that's actually one of the fundamental kind of like aspects of the rotary machine and how they work, as they have to like change electrical field and magnetic field constantly. Okay, so they have a synchronous reactance within them. These two, if you wanted to like look at the response of the sources from the mathematical models, not from the physical aspect that we talked about earlier, from the mathematical models, if you want to do that, that internal voltage and that internal reactance that they have is basically what's make up for that inertia and the support of the voltage and frequency. Okay, this if you wanted to like mathematically through the equations find out how it would support these internal voltage and that reactance would show up into that differential equation that we saw before that described, we said, like one of the parameters of inertia, and other parameters is damping factor, and another parameters is the force that we have, the external force that we have. We already gone over that briefly. So these are the parameters that actually uh, model those physical aspects. Now, this is how the conventional rotary machine works and the characteristics of those kind of resources. But what about the inverters? We already talked about that. The inverters are the switching devices. So what they do is you have a DC source of energy. You try to do the switching. We've already gone through the methodology and the control system. You do the switching and you change that DC system into the DC voltage or DC current to the AC voltage and AC current through the switching. Now, that being said, that instantly would tell you that, okay, the performance of an inverter relies purely on the switching devices and semiconductor devices. Okay, so there is no inductance in there. There is no magnetic field, magnetic or electrical field transition within the semiconductor. They are just cutting on and off the electrical field or electrical current. Okay, so they are based on a power electronic device, meaning the semiconductor and switches instead of that electromechanical energy conversion. Okay. And beside that, we already talked about that because of that nature, inverters cannot provide inertia. There is no actual physical concept of inertia in an inverter. So that being said, all the supports that the rotary machine could have for the voltage and frequency stability, because of that inertia, okay, and address the turbulence in the system, now inverters cannot do that, or at least they are limited by their own capacity, by the source, but by the DC source capacity, not their own, not the inverter. They are limited by the DC source capacity. Okay, so now another part of the difference, another difference between the inverter-based resources and rotary machine resources are the fact that they are purely have to rely on the control system to address the load's demand, either active power and reactive power. Okay, so the control system, that PID control or the droop control that we had in GFL or GFM grid following and grid forming, okay, those control systems are what actually decide, are the one that decide how much power we are injecting or how much reactive power we are injecting or consuming. So it's not an inherent or a natural characteristics of the system. It's actually a mathematical control. Is a artificial kind of like setting. So this is the major differences that creates some kind of like abnormality in the behavior of those resources regarding like compared to the rotary machine when we talk about the system analysis. Okay, now let's focus on our discussion here as a power flow analysis. In previous session, we already seen what are the equations of the power flow analysis. We said we wanted to like calculate what is the power, the active power and reactive power that is transferred from each between each two nodes in our system. Okay, we talk about that. We run a KCL and after all those thought and processes, we reached out to the two equations, one for active power based on the characteristics of the two nodes that we are wanted to like analyze, and another one was the reactive power, and we find these equations. Now, what will happen? What would be those characteristics of the inverter-based resources that we talked about would affect the variables in these two equations? Okay, how the inverters would affect these variables in this equation, because these equations are created by the conventional model of power system. So they are suitable for rotary machine, but what about the inverters? How they would affect these variables? Now, one part is that we said every time that we wanted to like talk about a power system analysis, every node or bus that we wanted to like analyze, we have four variables. Two of them are known and two of them are unknown. And based on that, we describe our buses like as PQ buses when the active and reactive power of the bus is known, or PV buses when the active power and the level of the voltage, the amplitude of the voltage are the known variables, and slack buses when the voltage and theta, the phase angle of that, the phase basically of the that node is known. So we have those three references. But when we talk about the inverter-based resources, okay, it's really hard to consider any of those categories for inverters. Why? Because they do not nearly fit into either PV or PQ. Okay, this is not why is not anyone can guess why we can't, for example, if we have a grid following inverter that measures the demand and try to address whatever measured the demand measured in the terminal, okay, based on that PID controller that we talked about. This was the grid following, and they had a PLL for the frequency synchronization. Okay, why we cannot consider the grid following inverter as a PQ bus. When you have a bus that is connected to the grid following inverter, why we cannot connect purely consider that bus as a PQ bus? Anyone can tell me, or PV bus, doesn't matter. Anyone can tell me or guess why we can consider P and Q as known or P and V as known variables when we have an inverter on that bus. Think about how they work.
Because it's constantly changing because it's reading the grid, following, so you can't describe it.
Half.
Yeah.
Okay, it's constantly changing is not quite true because rotary machine is also constantly changing because they have to address the variation in demand. Okay, not as fast as inverters, but they are changing also. Okay, but the second half of your statement was true because they have to read the voltage variables from the terminals in order to calculate the P and Q. Okay, so basically PQ, what was PQ? PQ was the fact that, okay, the boss, the active power and reactive power are known. Now we want to find what is the voltage and delta, or like the theta. But when we talk about the grid following inverter, without knowing the voltage, the grid following cannot understand the P and Q. Okay, so it relies on the unknown variable to know the variables that's supposed to be known variable. Okay, same goes for the PV bus. Now, how about grid following? Grid forming, sorry. How about grid forming inverters? They were different. They were dictating voltage and frequency. Remember that the loop control was for dictating voltage and frequency. Why we cannot consider a grid forming connected bus as PV or PQ? Any idea? Guys from Zoom meeting, you also can participate if you want, if you have any guess or like any idea. No? Okay. Let me review the concept of grid forming. What was the grid forming? What the grid forming do? It dictates the voltage and frequency, or the voltage and phase. Correct? Now, we have a bus. There is a source, the grid forming inverter connected to the bus, that source dictates voltage and phase. What category of the bus that would be between those three categories? PQ, PV, and slack? It is slack. So grid forming wanted to force the bus to be a slack bus. Okay, so it's not going to be PQ or PV. So let's say we have 10 buses in our system, 5 of them are connected to grid forming. Now what we have is that 5 of the buses are forced to be a slack. While we know that we only in our power analysis, in the general methodology that we developed, we only had one reference. Now we have multiple reference. And although they wanted to like support the system, but because they are locally kind of like mandating those variables, there is no they are necessarily compatible with each other completely. There are going to be some errors between them. Do you understand what I'm saying? So like the grid forming one wanted to like have the voltage as 1 kilovolt and 60 hertz frequency. Okay. But that doesn't mean that the 1 kilovolt and 60 hertz frequency that I, as a grid forming one, would measure is exactly the same 1 kilowatt and 60 hertz frequency as the second grid forming, like down, like on up in Edmondwood, measure. They wanted to like do the same thing, but that doesn't necessarily mean they actually doing the same thing. So that makes some problem in the referencing part, the slack bus. Now, beside that, we already said yes, grid forming want to dictate the voltage and frequency, but how they work? How they work when they wanted to like calculate the or dictate the voltage and frequency? What was the input in the control system of a grid forming inverters? Do you remember what was the droop control do? What was the equations of the droop control?
With changing frequency.
The result is to keep the frequency and voltage at the same level. What they do is that they measure the demand for the active power and reactive power, okay? And they try to like address that demand so they keep the frequency and voltage at a certain level. Does that make sense? Are we good for that? So now, what that means? What are the known variables on that parameter on that control system? Active and reactive power. So now you have a slack bus that relies on PQ. Now, how the inverter control addresses understand PQ? They have to measure the voltage and current or the frequency and voltage at the terminal to calculate what is the reference P and Q is, so they could set their own V and Q. So do you see the loop here? So we have a slack bus which is supposed to be V and delta, voltage and phase should be known, but the reality in the control system is that the input is voltage and delta who calculate the P and Q and demand that voltage and delta. You know what I'm saying? Do you see the cycle? So known variable, to address the known variable, you have to know the unknown variable, who's the function of the known variable. Again, it's kind of like a nonlinear, kind of like relationship within that parameters. So they don't, but we remember the droop control was a linear control, it was a line. Remember the curve of droop control? Now, when we have a power flow analysis, we are dealing with a nonlinear equation, which basically that means we cannot do that by Newton-Raphson. Newton-Raphson was also a linear method. So that means we are going to have a hell of a trouble in order to find out what is the accurate answer is because of that nonlinear behavior of those inverters. Okay, now this is one thing. Another thing is the absence of the inertia and damping, which we already talked about that would also affect the power flow analysis. And another part is the reactive power behavior. We said the level of the voltage is it would respond to the level of the reactive power, injection or consumption. Okay, so now if we have an infinite amount of capability for delivering reactive, then we don't have problem. If the voltage drop, it automatically drain the reactive power and adjust the voltage. If the voltage goes up, it automatically consumes the reactive power and adjust. But as we know, in inverter-based resources, we have a DC source which has a capability. There is a cap on how much current and voltage we could provide for our DC system. There is a limitation over there because of the devices or the switches. So if the inverter even want to draw a massive amount or like a notable amount of reactive power while providing the demand active power, then we're going to have a problem because it would exceed the level of capacity that our DC part has. So now inverter would face limitation on providing reactive power, meaning we are going to be a little bit shaky on stabilizing the level of the voltage. Are we good? So these are the parameters that would affect the power flow equations. Are we clear so far? Now, let's go a little bit deeper into that discussion. In grid following, we said the internal structure is, first of all, we have a PLL that tries to synchronize the system. Then we had an outer power control loop, okay, that decides the active power, reactive power injection, okay, and we have an inner current control loop that regulates the output current because we don't want it to exceed the amount of power that the switches would tolerate, or like it is basically that current control is, we already talked about, is sort of protection for not failing the devices. Okay, so that being said, basically what we are talking is that we are deciding about the current injection based on the demand. So what the inverter do from power flow perspective, from power and injection perspective, is that it decides the reference current that you have to have, okay, based on the PQ and the voltage at the terminal. Are we good? We already said that PQ relies on the voltage to understand the references of the inverters, because to be PQ boss, you had a paradox because they need voltage. Okay, that's where that paradox came. We need the voltage to transfer PQ to the actual parameter that the inverter works on. Okay, now what would be the impact? So we already talked about that. Now our system would not be actually PQ or PV or any kind of like type of this. It works as a semi PQ because yes, it would define PQ, but it also relies on one of the unknown variables that we have as our voltage. Okay, now that, as we talked for the grid forming inverters, creates a nonlinear behavior into our system. And beside that, if we have a fault or any kind of like variation or sag in our voltage, that means basically our control system would either saturate it or shut down because it wanted to like address that while addressing P and Q. Okay, and basically means that okay, control the inverter is now do not respond or is saturated and responds in a wrong way. Okay, so these are the problem. Now, this is the impact on a power flow. We already talked about that briefly, the constraint and limitation within the inverters, which is basically the constraint and limitation of the control system. We said we have a maximum ultimate. We can provide infinite amount of power. There is a current limitation in the inverter-based resources. So that would affect our system, our response. And another one is the PQ curve. We already also talked about that. It's a nonlinear kind of like behavior. And we it is gonna be hard to follow the nonlinear function with a Newton-Raphson method, which is a linear numerical method. Same kind of like concept goes for the GFM, the grid forming. They are different, but basically, I think as also you already seen in your reading assignment about duality of grid forming and grid following, the paper that I uploaded in Canvas, you already, I think, I assume that seeing that duality and the similarity between these two types, that similarity is also the reason, the cause of having same problems on power system analysis, in power flow analysis, when we dealing with the grid forming inverters. Now, I already talked about that on the previous slide, so you can go over that. I already upload this PowerPoint to the Canvas, so I don't want to like repeat all these points that we already mentioned earlier in the previous slides. Now, what would happen to our power flow analysis if we want to adapt to the new situation? Now we have new type of resources. Okay, what would affect how we could modify our power system analysis, our power flow analysis that we develop for conventional system in order to address the problem with the inverters. Basically, for GFL, because we are controlling the current injection in the system, instead of dealing or like assuming a GFM as a PV or a PQ, generally PQ is the one, boss, we have to replace all those P and Q function that we had in power flow analysis with now new variable that actually exists in an inverter-based grid following inverters into the system, which is that current. So we have to like replace all those P and Q's on the functions of the power flow analysis, that Jacobian matrix and all those things, with the current that we have in the inverters. Okay, and same goes with the grid forming. Now we are enforcing voltage and delta. So now we can't consider them as fully unknown variable in a PQ buses. So we have to replace the functions that we had before. We had the F function as P balance, P plus P generation minus PD was equal to 0. Remember that? And same for Q. Instead of this function in our Newton-Raphson method, now we have to consider the conditions of the grid forming and replace it with a suitable function. We are going to see that. Now, in order to do that, in normal Jacobian, let's say PQ buses, that was our Jacobian matrix in the method, in the power flow analysis. Okay, we had like, for example, this is two bus. Okay, round off the differential equation of the P over one of the unknown, which is delta, P over another unknown, which is V, Q delta, and QV. Okay, that was our Jacobian matrix, if you remember. Okay, now we said in GFL we have to replace the P and Q functions, these functions, these P and Q, with the current values. But it's not simply a current. Current here is a complex value. P and Q are not complex. So how we deal with that? We replace P with the real part of the current, and we replace Q with the imaginary part of current and do the differential. Are we good? Is not is very simple, but we are gonna see. I have an example in the upcoming slides. For our grid forming, instead of having a demand generation and transfer function that we had, that f that we had. Remember that f before was pi plus p generation minus pd, p of demand, and this should be equal to 0. Are we good? That was our function, our criteria of the Newton-Raphson, how we could count if our guess is close enough to the real value. That was our criteria, our condition of the method algorithm. Okay. Now, this is only a function of P, but we said in group controls, we are insisting the voltage and frequency. So now we have to have a function that considers that. So now we change that function into a function of V and P because of that discussion that we have. And instead of power balance, we consider the droop control because that's what demands that is the rule of working. Okay, that is the nature of our work with GFM. We use the droop controls functions instead of the power balance function that we have. So instead of P, we have function of V and P and function of P and delta and P. Are we good? So now we don't have one P to round. It is not round P to round V anymore. Now it has two functions. Are we good? So, and you can see now because V and P are known, here we have round F over round V and round F over round Q. Here we have round G over round delta and round G over round P. Let's see how it works. Let's say we have a three bus system. One of them is a slack. The second bus is connected to a GFL, the grid following, and the third bus is connected to a grid forming unit. Now let's see how the Jacobian works. The blue one is the general Jacobian. If you have these three system bus and wanted to like follow the general power flow equations, that would be your Jacobian. We have this is the slack bus, so we know the V and delta, and we know that this is 1 per unit and delta is 0. Okay, so the Jacobian would be P2 over delta 2, P2 over V2, and same delta and V3, Q for them, P3 over those unknown variables, and Q3 over those unknown variables. Now, the second bus, which is this part, we said is GFL, and we said we have to replace the power, active power and reactive power with the real and imaginary part of the current. Are we good? So what we do is instead of round P2 over round delta 2, we have round real part of current this is a real part of current. Sorry, I draw over the R. Over the delta, real part of the current over the V2, same for the V3 and delta 3. And for the Q, we replace the imaginary part of the current for the bus 2, and the denominator are the same. Now, for the grid forming, we said we are going to replace that with that F and G. Look at this F and G. F and G. See, P has a coefficient here. Do you see that? V also exists in this F. So if you want to differentiate, we are talking about the chain differentiation of the F of G of X. Okay? What's going to happen? If you differentiate that function based on P, if you replace this P with that F and G, as we said in the previous slide, and now do the differentiation based on delta 2, you have a new variable. That MP was, if you remember, that was the coefficients multiplied by P. So it's come out of that function. Same goes when you wanted to like divide by round V for delta 3, for VT, V3, and same goes for the Qs. Now I want you to actually drive the functions. I already gave you the functions. Okay, replace those functions into the Jacobian. Do the partial differential and see these coefficients where the coefficients come. So see, this is MP minus MP. Here we have 1 minus MP times that differential. Here we have 1 plus MQ times that differential. I want you to like go and actually drive that differential or that F and G and try to like find out, okay, where these coefficients and this formula came from. Are we good? So this is how we could modify our Jacobian to address all those differences or the problems, if we want to call it, that inverter-based resources would add to our power flow analysis compared to the conventional rotary machine. And this is kind of like the general differences. Like we basically replace, we already talked about that. This is the summary of what we did in modification of that Jacobian. Are we good? Any question? No, it's pretty straightforward, but you have to like at least once you do the mathematics, so you get familiar with that. Okay, and you are more comfortable with where that MQ and P and where that one come up, in the Jacobian. Okay, these are the summaries. I don't want to like bore you again with repeating over and over again. You can go over the slides and find out the thing. And I also summarized the impacts or the comparative analysis of the GFL and GFM for power system analysis into this table. So basically, the reference of the generation in grid following, we follow the external grid. Grid forming, we create our own reference. Dependency, grid following, we know that it requires a fixed grid or like a stable grid or like a strong grid, whatever you want to call it. Grid forming can operate by themselves. We already said that. We already talked about that. In power flow bus type, grid following works as semi-PQ bus, where the grid forming works as a, I'm saying semi because of the discussion that we had, semi-PV or a slack bus. Okay. Voltage supports grid following is very limited. Grid forming, because it wanted to like dictate the voltage, is a little bit stronger, but we already talked about that, and you already seen in the reading assignment that duality, that although we officially say that grid forming are strong on voltage, but in reality there is limitation, and that limitation is that Q capacity limitation that we talked about. Okay, that reactive capacity. Same goes for the frequency support. Okay, we already had a discussion and you already read that in that paper. For black start capability, it's not related to power flow analysis, but we already know that the GFL cannot have the black start, GFM can, and mathematical complexity. Again, that nonlinearity that it adds, you already seen in a Jacobian matrix, the nonlinearity it adds. GFL is moderately complex, but GFM is completely nonlinear, huge difference. Okay, so and in order to do that, you have to have like a consideration based on what we discussed. There's a consideration that we have to take into account. First of all, the initialization. Now we cannot just when we have GFM and GFL, we can just the initial guess cannot be just haphazardly chosen because of the nonlinearity in the system now. If you choose a very diverted guess, you might end up kind of like actually getting away from the true answer rather than the conversion to the answer. Okay, this is one part. The iteration is now different because it's nonlinear, is not just following the Newton-Raphson, because sometimes Newton-Raphson could actually shoot you away from the actual because of the nonlinearity. Okay, now that has a problem. The damping factor also could help if you want to like address that problem. There is some solutions you can search on that. The enhanced Newton-Raphson solution for nonlinear behavior of the inverters. There's tons of like those videos and papers. I will try to like find and post the good ones for your uh, deeper kind of like study. And the convergence criteria is also one of the tackles that one of the problems that we have to tackle when we talk about the power flow analysis, when we have IBR dominating the system. Again, that's the result of the nonlinearity and that chaotic behavior that could happen because of that nonlinearity in the function. Any question? Are we good so far? Guys in the Zoom, any question? No? Okay, if not, that's the today's session. And have a great rest of the day.